Let's explore this idea of density dependence in this following way. Let's map out the rate of change as a function of the abundance or density of the population, where we're going to put that on the x-axis, abundance or density. Abundance is just density is just the numbers per unit area, and the rate, like the population growth rate. The per capita growth rate, as I showed earlier on, is actually the balance between the per capita birth rates and the per capita death rates. That was in the very beginning where I showed the continuous form of the exponential growth model. So we can break down birth rates and death rates as being a function of density. So for this example, let's just imagine that the birth rate is dependent on density, so that as the density of the population increases, the birth rates decline, the per capita birth rates decline. So the average individual is making fewer and fewer babies as the population gets bigger and bigger. And you can imagine a lot of situations where that might be the truth. On the other hand, the death rate maybe is constant across this range of density, the per capita death rate. So in this illustration here, the birth rate is density dependent. It's dependent on the abundance of the population. I'm going to write that as DD. Okay, and the exclamation point is just because I think it's important. And the other one is DI, is density independent. It's flat. Independent means it doesn't change as a function of density. And where those two things intersect, the rate, the per capita rate of birth and the per capita death rate, sets where the population equilibrium is going to be. If the population rate, if the death rate is lower, as I've depicted here with the second line, then the intersection between those two lines, the death rate and the birth rate, is going to be in a different place. It's going to be right there, and if you drop the line down, the abundance is actually at a slightly higher place, which makes sense. If we've just decreased the death rate there relative to where it was before, the overall population abundance should be higher. So the equilibrium point is actually set by the balance of both density dependent and density independent factors in this case. And the important thing to notice here is that for something to be density dependent, some rate needs to be changing as a function of density. And in this case here, and it's just in this case here as I've drawn it, I've chosen birth rates to be density dependent. I could have drawn death rates to be density dependent. Maybe death rates increase as a function of density. That certainly would make sense as well. Maybe there's starvation or something like that. Or maybe both birth and death rates change as a function of density. Certainly both realistic examples. And so in the future examples that we're going to talk about is, does density dependence actually exist in populations of insects? And is that one of the features that causes regulation, that prevents populations from going to infinity and prevents populations also from getting too small?